have a question that involves a collision with a linear moving object, an object with translational momentum. So we've got a little ball here, 1 kilogram ball moving to the right at 10 meters per second. And it's going to collide right at the tip of this hanging rod. Now the rod is hinged at the top. So it's going to swing, and you can see that it swings in this arc after the collision. So there's going to be some angular data in here that we're going to have to deal with. Now, when you read any AP question, you have to read really, really carefully. Now, when you look at this thing, and I apologize for the small print, but hopefully you have it in front of you. When you look at this question, it says, first of all, it's initially at rest. That bar is initially at rest before we begin. So I'm going to highlight that. So we know it's at rest before the collision. And the second thing, it literally tells you that linear momentum is not conserved. But it doesn't say anything about angular, and angular momentum will be conserved, and we'll talk about the reasons for that in a second. The other thing it tells you is kinetic energy is conserved. So in other words, there's no losses. It's going to be a perfect collision, and all the kinetic energy before is going to equal all the kinetic energy after of that system. Now they give you the moment of inertia for the rod, they give you an equation for it, ml squared over 3, and they give you the mass of the ball and the speed of the ball, etc. So let's discuss some of the physics before we begin. Now, during the collision, why is linear momentum not conserved? Well, linear momentum is only conserved if there are no external forces that hinder the process. And if you look here, you've got this little hinge acting on the second mass involved in the collision that's going to prevent it from moving left to right. It's just going to be able to swing. That's it. So it's not going to have any translational motion. The other way to think about it is that if you look at and I've got a simulation here, hopefully we can see that. If you look at this simulation, it shows a collision between ball 1 and ball 2, and this little X here shows the center of mass of this system. And now this is a conservation of translational momentum. So when I play it, watch what happens to that X. So imagine that's the balance point. Clearly ball 2 is bigger than ball 1. That's sort of the imaginary balance point of that system. And when I hit play, X just continues to move to the right at the same speed before and after the collision. So that has to be true for linear momentum to be conserved. That's also true, by the way, if you did a collision that involves 2 dimensions. So here I see 2 balls are flying at each other at different angles, but it's still linear translational momentum. Watch the X. So it's moving down to the left. It just continues to move according to Newton's first law. Now it changed there when it hit the wall, but while the other objects were free to move, in the absence of any other forces, which means before it hits the wall, that little center of mass will continue to move from upper left to lower right. Or sorry, upper right to lower left. So now let's go back and see what we can do with this question. So what is true? So we know that the sum of all the angular momentum before has to equal the sum of all the angular momentum after. Any collision, that's got to be true. Now, angular momentum is only conserved if there's no external torques present after the collision. And we'll talk about that in a second. But clearly, the only force that's causing this thing to swing is the ball. The hinge does not exert a torque because it's the force that acts on the hinge is right at the pivot point. And we know that that won't exert a force. So there's no external torque acting on this. So momentum before is momentum after, angular momentum. The other thing is true is kinetic energy is conserved. So the sum of all the kinetic energy before the collision has to equal the sum of all the kinetic energy after the collision. So that could help us too. Now the final thing that's true is after the collision, if we just look at this rod, it just starts to swing freely back and forth. It becomes a pendulum. And we know that just for the hanging rod, anytime it starts to swing back and forth, you can imagine it as this long pendulum. We know that conservation of energy holds true for there as well. So the sum of all the energy at the bottom has to equal the sum of all the energy at the top. All right, so now we've got all our physics organized. Let's see if we can organize our answers. says A, determine the angular velocity of the bar immediately after the collision. All right, well, now you could write the equations down, but let's just imagine it. My total angular momentum before will just be the ball, and later on I'll show you how to calculate that. My total angular momentum after will be the tangential component of the ball's velocity times the radius. That's going to help us get the angular momentum of just the ball after, plus the initial angular momentum of this rod. Now, I don't know the final velocity of the ball, nor do I know the final angular velocity of the rod, which is what we're looking for, but there's two unknowns there. So I don't know. I think that first equation might not help us initially. What about kinetic energy? I can certainly calculate my total kinetic energy before, but my total kinetic energy after consists of the ball moving down at an angle, so I need to know its velocity, and the rod spinning up. Again, I've got two unknowns. So I'm going to focus on my last equation. I can figure out my total energy before the things collide of just the rod, and then figure out my total energy after the rod swings up. So right after the collision, the rod's got some kinetic energy at the bottom. So at the bottom, the rod's kinetic energy, because it's rotational, is given by this. So I've got kinetic energy rotational, that's my initial energy of the rod, has to equal potential energy of the rod after. So the rod at the bottom, once it gets hit, it's going to start to move to the right, swinging upwards, just like a pendulum. And that kinetic energy is going to get converted into potential. So because it's rotational kinetic energy, it's not a point mass. It's not like the Tarzan swing. It's a rod that's got a distribution of masses. I can't use 1/2 mv squared because the mass is not all concentrated at the end. So I've got to use my rotational one. 1/2 I omega initial squared. And that's what we're looking for, that initial angular velocity. And all of that's going to get converted to mgh. All right. Now they give you I of the rod, ml squared over 3. So I've got 1/2 ml squared over 3 is I. And they give you the mass of the rod, it's 3 kilograms. Omega initial squared equals mass of the rod, right, still 3 kilograms, times g. And notice they tell you to use 10 for g, must have been an old AP exam, times the height at which the rod rises. Now you may be inclined to put 1.2 for that height, but remember when you're talking about potential energy, you're looking at the center of mass. How far up does the center of mass go? And if I look at my picture, the center of mass of this rod initially is at the halfway point. It's a uniform rod. So if I track that center of mass only rises this far. So that's the key to this question. Your height that it rises is half of 1.2. So it's 1.2 over 2 or 0.6 meters. So once you get your height as 0.6 meters, all is good to go. Your masses will cancel and you can work out what W initial is. And you should get 5 radians per second. Now let's move on to part B. Part B, it says determine the speed of the 1 kilogram object immediately after the collision. Well, again, if I want to use this angular momentum formula, I can get my total angular momentum before, and I can even get the angular momentum of the rod after, and I could work around and try and figure out what the angular momentum of the ball is or what the speed of the ball is. But really, all I'm going to get, because angular momentum is always related to these tangential components. So let me give you an example here. When I go from linear anything to angular anything, it's always at a tangent. So for example, if I want to find out the velocity based on the angular velocity, I multiply it by r. But what I'm actually getting is the tangential velocity. If I want to find the acceleration, I take my angular acceleration and I multiply it by r, and that's my tangential acceleration, velocity at a tangent. It's the same thing for angular momentum. Angular momentum is related to linear momentum times r, but this linear momentum is always at a tangent to the circle. And So in order to use this angular momentum equation, I'm going to end up calculating the tangential velocity final. And if I want to get this overall velocity, I need to know the angle. So even though it's marginally useful, at this stage, I don't have the angle. So I still can't complete it. So I'm going to look at this. I know this sounds awfully complicated. I'm trying to give you as much sort of information as possible as to what to look for in these questions. This is a significant question, this one. So they tell you, and I think if they're going to tell you that kinetic energy is conserved, then you can bet that you're going to have to use that concept. So my total kinetic energy before is just the ball. So K initial, and that's going to be just the ball, is going to be K final of the ball because it's still moving, plus K rotational of the rod. So kinetic energy of the ball is 1/2 mass of the ball times V initial squared, V initial being 10 meters per second. Kinetic final of the ball, same thing, 1/2 m ball, V final squared, which is what we're looking for, plus the rotational kinetic energy of the rod. And we know the formula, 1/2 I omega final squared. And if you look at the previous question, we already have omega and they give you I, so you have everything in this formula except for that velocity. So you should be able to solve for it and you should get 8 meters per second. Now remember, kinetic energy is scalar, so what you will have figured out there is the overall velocity final of that ball. So this little vector here, if the answer is 8 meters per second, that little vector there is going to be 8 meters per second, right? It's a scalar quantity. Now, if we look at part C, determine the magnitude of the angular momentum of the object about the pivot just before the collision. Okay, so this requires a little bit of explanation. Let me just clean up my picture a little bit. If you want to convert a linear motion like the ball before, like the ball was initially moving like that to the right. Just before it hits the rod, we know the rod is going to start to swing up in this circle. So the angular momentum, if I want to convert that to an angular quantity for this system, I need the tangential component of that velocity just as it hits. Well, fortunately, it hits at 90 degrees to the rod. So it's like that. So when I find my initial angular momentum, I'm just going to take my linear momentum and multiply it by the radius. And as long as P initial is tangential to that arc, we're good to go. In other words, I want P initial and R to be 90 degrees to each other, and they are in this question. So part C is actually pretty easy. I would simply go M ball, V initial of the ball, which are both given, right? So the mass of the ball is 1, the velocity is 10, so my initial momentum, linear momentum, is 10 times the radius, times 1.2. And you can see that 10 times 1.2 gives you 12. So we're almost there. Now the last one, finding the angle theta. If you want to determine the angle theta, now we can finally switch it up and do our conservation of angular momentum. We have everything we need now. We've got all of our values in place. We know what the hypotenuse is. It's going to be 8. What we're looking for is this little blue tangential component here. So for the very last one, we want to do conservation of angular momentum. Now I'm going to have to erase some stuff so that we have some room on the screen here. So let me move all of this stuff out of the way. Almost there. And we'll just set it up. So this is for part D. And in part D, I'll do it in blue. We're using conservation of angular momentum. So my total angular momentum before is the initial angular momentum of the ball, which is calculated in part C. Notice how D uses the previous one. That's common on AP. And my total angular momentum after is the final angular momentum of the ball plus the angular momentum of the rod. Those two things are moving in a circle. So we know the left-hand side is 12. My final angular momentum of the ball will be mass of the ball times v final, but you got to remember that's going to be the tangential velocity final times the radius, which we know is 1.2. And then the angular momentum of the rod, anything that's moving in a pure circle like that, we can switch and use the traditional angular momentum equation, which instead of mv for linear, it's I omega. And we know both of those things, right? Omega final was 5 radians per second. I is ml squared over 3. So in this equation, we know everything except for that. And if you go ahead and do the calculations, you guys can check your work as you go. You end up getting final tangential velocity of 4. So you can check that as you go. You should get your final tangential velocity of that ball being 4 meters per second, and then you can get the angle. So if I clear some space up top, this is what we've come up with. So if I just look at this little vector right here, I know the hypotenuse from previous questions was 8. I will have figured out using this conservation of angular momentum that this side is 4. And then you're solving for that little theta there. So it looks like it's going to be cos. So cos theta is 4 over 8, and you should get theta is 60 degrees.